Welcome to what I believe is the fourth Helz Distinguished Lecturer Lecture. The concept of the Helz lecture was created by a donation from George and Roz Helz, who are sitting there. They should stand up and take a bow. Just a few words of thanks for creating the endowment that allows us to do this. We had a few missing years due to COVID, but I think we're back on schedule now. George, as you may know, served in the Department of Chemistry and Biochemistry for some number of years. I guess when he started, chemistry had a big geochemistry program. Chemistry kind of let geochemistry fade away, and so George became more closely affiliated with the geology department, I think it's safe to say. Roz spent all of her professional career at the USGS, and she is a person that many of us have worked with respect to, in particular, rocks from Hawaii. So thanks again. You're moving to California, so we won't be seeing you again at these events, perhaps. I also want to start off by thanking Phil Piccoli and Todd Karwoski, who were responsible for many of the details of this event, so give them a round of applause. All right, so it is my extreme pleasure to introduce somebody that I've known for decades. That is Alex Halliday, and I've got some stuff to read about Alex. So Alex is currently Professor of Earth and Environmental Sciences and of Climate at Columbia University. And perhaps very importantly for this talk, is founding Dean Emeritus of the Columbia Climate School, which some of us have discussed as a possible role model for building a much more cohesive climate program on this campus. Alex comes from Cornwall, England. Are you the guy from Penzance? From Penzance, but he's not a pirate. And he obtained a BSc in geology from Newcastle upon Tyne and a PhD in physics from the same institution, correct? Let me know if I get anything wrong. I've got a 37-page CV to read through, so deal with it. So upon completion of his PhD, he spent 10 years at the Scottish University's Research and Reactor Center. He was then a professor at the University of Michigan, which is when I met him. He then moved on to ETH Zurich in the late 1990s, and he then subsequently moved to Oxford University. And let's see, when did you arrive at Columbia?
2018.
2018. So he was director of Columbia's Earth Institute, and he was also Oxford University's Dean of Science and Engineering, and he's also been vice president of the Royal Society. So Alex is a well-known isotope geochemist. Some of the people that I talked to about Alex, you know, they weren't all that familiar with his science, but I pointed out that he was the first person to acquire a multi-collector inductively coupled plasma mass spectrometer. And that got their interest up because MCIC-PMS is kind of one of the most important analytical tools we now have in the world of isotope geochemistry. So he was the first. And I guess I saw it when it was being constructed, and I thought it was a really stupid idea. And that tells you something because now they've sold hundreds of them. So it turned out to be a really good idea. He's also known for his work on the timing and processes of planetary accretion, core formation, and volatile loss in the terrestrial planets. And he's also worked on a huge range of different topics, ranging from silicic volcanism, mineral deposits, ocean tracers, climate change, pollution, and human health. He has many impressive credentials in his CV, and I can only read through a few of them here. He was president of Geochemical Society, is president of the European Association of Geochemistry, and he was the Volcanology, Geochemistry, and Petrology section president of the American Geophysical Union. He has many honors. I won't spend 10 minutes reading those. I'll point out he's a fellow of the Royal Society and an international member of the U.S. National Academy of Sciences. He's the recipient of the Murchison Medal of the Geological Society, the Urey Medal of the European Association of Geochemistry, the Oxburg Medal of the Institute of Measurement and Control, and both the awardee of the Bowen Award and the Harry Hess Medal of the American Geophysical Union. That last one is a really good one. It's a really important one. And last but not least, Alex is a knight, so you have to address him as Sir Alex. Alex's CV as of January lists 422 papers. I'm only going to read the titles of 2 of them. And these are 2 of his latest ones, and I do this to let you know just how diverse Alex's science is. One is titled Metal Impact and Vaporization on the Moon's Surface, Nano-Geochemical Insights into the Source of Lunar Metals. That sounds like a good one. I like the moon. And the second one is Comparison of Urinary Potassium Isotope Signature in Cancerous and Healthy Pancreas. That sounds like a real award-winning title. And I guess you want to make sure you don't mix the samples up, right? Okay, so without any further ado and bad jokes, I will turn the podium over to Alex, and the title of his talk is up here, Climate Change, an Academic Imperative. Alex?
Well, thank you very much. Can you all hear me? Okay, yeah, good. So, so most of my research through my career has been in geology, and I guess 25 years ago, with multiple collector inductively coupled plasma mass spectrometry, I realized I could get into cosmic chemistry and early solar system stuff on the one hand, and a little bit of stuff to do with the recent history of the Earth and climate and ocean circulation on the other. And so I've gone all over the place scientifically. One thing I haven't done is become a real climate expert. And I'm going to talk to you today about climate, not because I'm an expert, but because I really believe it's important. And when I was vice president of the Royal Society, the Paris Climate Accord happened. And I realized at that point that I really wanted to do anything I could to help solve this massive problem of how do we decarbonize. So that's why I moved to Columbia in 2018. And I said, my predecessor was Jeffrey Sachs, who, as you well know, is a world-leading economist who knows half the world's leaders on first-name terms. And I'm nothing like that. But I said, if you want me to work on climate and taking this great organization of Columbia University's research, taking that in the direction more of climate, then I'd be happy to help. And so I'll start off talking about climate, and then I'll end up talking about what we ended up doing, which is to build a climate school at Columbia. And happy to take questions about any of it. But the main thing I wanted to impress upon people is how really scary the future looks in terms of climate change, not because of what we're predicting, which is bad enough, but what we don't know. And the gathering sense among the scientific community is that we may be being too conservative about the future and how it might change. Okay, so these are the 6 things I'm going to try and get through in 50 minutes. And you can see that most of them are going to show this rather sad-looking picture as a backdrop. I'll start off talking about changes in past climate as the first thing. And I thought I'd start off as a geologist should with James Hutton, who was the founder of modern geology. And he established what we call the principle of uniformitarianism, which is the present is the key to the past. And he basically went on to show that basically you could take rocks that are forming today, like a glacial till in Greenland, and actually see similar things in the past. And that's kind of more or less what you see. So this is a 700 million year old probable glacial tillite from the Kingston Peak Formation, which you can then sort of use the present day understanding of how these things form to figure out how they formed in the past. But then I wanted to introduce you to another person who you've probably all heard of as well, Harold Urey, who won the Nobel Prize for discovering deuterium, but subsequently moved into many, many different fields, including the origin of the moon, the origin of life. But he also worked on stable isotope geochemistry. He was the first person to realize that you could actually take carbonates and figure out what temperature they formed at. And this was in 1949, he said this. And this was the same year as Lamont-Doherty Earth Observatory was founded. You could actually use the oxygen 18-16 ratio to tell you about the temperature at which carbonates have precipitated. Now, of course, it's more complicated than that, but it involves looking at deep sea cores like these, sampling carbonates, and from that record, you can end up with a curve like this, which came out last year. It's a mixture of oxygen isotope data, some other thermometers like magnesium-calcium ratios that are used. It involves a certain amount of climate modeling to get these curves and to try and see what trends are more likely. So there's a probability function around this as well. But it actually shows you for the last 10% of Earth history, over most of the Phanerozoic, that climate in terms of temperature has gone up and down dramatically. And what you can see is that one of the things I think that previously people had thought was that over the Phanerozoic, the temperature of the surface of the Earth had gone down gradually. This doesn't show much sign of that. What it shows is a systematic way of regulating climate backwards and forwards in terms of temperature. And we'll come back to what that is and what controls that in a minute. But in the meantime, I think up here it's actually got the cooler climates and the warmer climates in dark green through to sort of a dirty red. And you can see that these things are roughly evenly distributed. There's about roughly the same amount of each of these things going across this curve. And you can also see that there are certain times, like today, when the temperatures are relatively low on the surface of the Earth. And that's true back here, about 300 million years ago. There are these dips, and some of them are quite dramatic dips, as you can see through the geological record. Now, you can combine this with the observations of glaciation, which we talked about with, of course, James Hutton and what he talked about, that actually in terms of using the present as the key to past, figuring out when there was glaciation in the past, you find ice rafted debris, and you can tell when there was the maximum extent of ice sheets from that ice rafted debris using paleo-reconstructed continental distributions across the globe. And what you can see is that actually these ice sheet extents pretty much correlate with when you've got these low temperatures in 018. So there's a very nice agreement with field geology observations, if you like, and what we see from oxygen isotopes. Now, the main driver of this is carbon dioxide, and I want to talk a little bit about why we know that. So if we just now zoom in on the last 1% of Earth history and go back the last 50 million years roughly, you can see in detail that the temperature is really, really high relative to today, back on the surface of the Earth. There were no ice sheets at that time. If you then look at around this time here, the Eocene-Oligocene boundary, which is about 33, 35 million years, you see the first signs of ice-rafted debris coming from Antarctica, and we actually can see the onset of Antarctic glaciation associated with that. And then later on, this sort of gap in the record here, you actually see this continuation of a decrease in temperature and the onset of Northern Hemisphere glaciation around 3 million years ago, and that's when we started the ice ages that we all know about in the Northern Hemisphere. So this temperature change has been quite dramatic over the last history of the Earth, the last 1% of the history of the Earth. And there have been ups and downs in it, but basically, as well as constructing temperature, we can also reconstruct temperature curves. We can also reconstruct CO2 using a variety of techniques. One of them is boron isotopes, but there's others as well, using various organic molecules. And if you look at the CO2 record, this isn't quite the same in terms of the scale, but it's roughly the same. You can see there was a big peak in temperature back here. Well, there's a big peak in CO2 as well. This is actually calibrated in terms of color, in terms of temperature, relative to pre-industrial times. And you can see actually this very big peak in here and a gradual drop in CO2 over time. So that's been, gives a pretty good clear indication that CO2 is related to temperature. And you can see that in this record as well. If you take a look at this big record going back through the Phanerozoic, the authors also compiled all the data for CO2, and they came up with this correlation, which shows you that actually through the whole of geological time, but with a little bit of a scatter around the Mesozoic, which isn't quite clear, but certainly in the Paleozoic, that's the first part of the record, and the Cenozoic, which is the most recent part of the record, you can see that there's this correlation between CO2 and what's called global mean surface temperature. Now, that correlation is quite interesting. I'm going to come back to it later because the slope gives you the sensitivity of temperature to CO2. And what you can see here, that's calculated here, is that it's about 8 degrees. It's actually the temperature associated with temperature rise associated with a doubling of the amount of CO2. And that's a higher number than we're used to from other considerations. So let's just zoom in on the last shorter, most recent bit of Earth history. So now we're talking about the last 100 ppm of the history of the Earth, which is really through the last bits of the ice ages. And here you can see that this incredible record that was obtained by initially collaboration between the British and the Russians, and their fantastic science is global, always need to remember this. And they use radar techniques to actually figure out, and other techniques to figure out that there was a lake under the ice sheets there in the Antarctic. And this Lake Vostok eventually was drilled in a collaboration between America, France, and the United States. And they obtained drill core through this ice sheet, which allowed them to extract samples of air bubbles caught in the ice. And from this, they were able to deduce temperature using things like oxygen thermometry, but also measure the CO2 concentration as well. And you can see the CO2 concentrations go up and down in between glacials and interglacials. And this is the natural behavior of the Earth. When things are cold, more of the carbon dioxide in the atmosphere goes into the oceans, gets dissolved in the oceans. And when things are warmer, more of the CO2 comes out. So that's the natural behavior of the Earth through geological time. And this is what happens today. You can see that this natural systematic behavior has been completely messed up as a result of a huge increase in CO2 that's been developed in the last few years. And this is based on not just the Antarctic ice cores, but many other ice cores, as well as instrumental measurements of Mauna Loa, direct measurements of the CO2 concentration in the atmosphere. If you zoom in on when this happened, this is the last 1,000 years now, you can actually see there was a spike. This development of this spike really started at the end of the 18th century. And so this is a good pub in New York City. Boulton and Watt patented a new form of steam engine in 1769. James Watt is a very famous engineer, and he basically came up with a way of taking the condensation side of the engine out of the main part and actually building a separate condenser, which made it much more efficient. And this coincided with the development of the Industrial Revolution, and suddenly you had a way of generating vast amounts of new materials, relatively easy, extracting coal, etc., from mines, and the whole of the Industrial Revolution really kicked off. I would say this is a remarkable thing. If you look at the guys who won the Nobel Prize for economics this last time around, two of them wrote a book called Why Nations Fail 10 years ago. If you haven't seen it, you should take a read of it. But it's an incredible book explaining the role that societal behavior has allowed people to develop ideas, incredible ideas, including Bolton and Watt, where they were actually able to do something called patenting and actually have their inventions protected. And that's something that's been true of liberal democracies and been incredibly important for the development of humankind over the centuries. But anyway, so this guy, Bolton and Watt, basically developed this new kind of steam engine, and you can actually see this coincides beautifully with when we see this rise in carbon dioxide associated with emissions. And today we have fantastic records from NOAA and scripts. Well, for now we have fantastic records from NOAA and scripts, of course, in UC San Diego are involved as well through Keeling and his work, measuring CO2 directly from volcanoes, above volcanoes, I mean, Mauna Loa, and actually sampling the atmosphere very effectively. And you can see there's this up and down curve. This is a seasonal effect. The present day value is about 425 parts per million. Now, we've known for a long time that this is related to fossil fuel burning and in terms of energy. This shows you the last 65 years of increased CO2 emissions associated that we can actually see, and increased levels of CO2 emissions that we've actually got. And you can see that fossil fuel carbon dominates that quite dramatically. Land use change, which is things like deforestation, et cetera, that actually has been declining in terms of being a major source of CO2 contribution to climate. Now, the first person to actually figure out that CO2 is important in terms of changing climate, there are some European scientists who are often credited with this, people like Tyndall, et cetera. But actually before that, Eunice Newton Foote, who was a scientist and inventor, she became a human rights campaigner from Seneca Falls, New York, published this amazing piece of work. It was given a few years before Tyndall did his work, reported, of course, at the American Academy of Arts and Sciences by a man who had to do it for her. But she did these experiments on CO2 in different vessels and other gases, and showed that actually CO2 heated up tremendously, and had this prescient conclusion that actually the Earth at one time would achieve a higher temperature if there was too much CO2 effectively in the atmosphere, etc. So it is quite remarkable that that's only come to light fairly recently, that she'd actually figured this out before. And the mechanism wasn't quite the way we understand it today, the greenhouse effect, but nonetheless, she actually realized that was firstly the case. In 1975, a professor at Columbia University, Wally Broecker, who's basically published the first paper in the scientific literature looking at the effects of rapid climate change. They recognized that this was possible for the first time by looking at ice core records, ocean drilling records, and realizing that you could get changes from ice ages really fast, and temperature changes were possible on the surface of the Earth very quickly. And he coined the term global warming and was the first one to use it in the scientific literature. Another major breakthrough was associated with NASA Goddard. I know you've got a NASA center here as well. The Columbia University one, which is a Columbia University building just next to the Earth Institute above Tom's Restaurant, which you'll know from Seinfeld, is NASA Goddard Institute for Space Studies. And so the Goddard Institute for Space Studies has played a big role in terms of climate, not only producing a lot of the climate records and forecasting and the models, but also Jim Hansen, who was the leader for many years, and he played a huge role in terms of not just recognizing that not only was climate change going to be coming, it already was happening. And he made this clear to Congress in testimonies, et cetera, back in the 80s. So there's been a long history of people in America playing a major role in terms of understanding climate change science. And this is where we are in terms of global surface temperatures. This is the ECMWF data, European Center for Medium Range Weather Forecasting, and other involves Copernicus, et cetera, as well. And it gives you an indication from the 1860 here to the present day how much increase in temperature there has been. What's maybe more alarming is if you look at what's happening in terms of record number of days above 1.5 degrees, you can see that in 2024, we actually had 3/4 of the days were above 1.5 degrees for average for the Earth. So this is stuff we were talking about trying to avoid a few years ago, and now it's actually on its way and feeling quite like it's about to happen. Of course, there are annual cycles or cycles that happen over a few years, and so these numbers might come down again, but at the same time, it's very clear we're on a terrible trajectory, and it's happening fast. So I want to talk now about climate impacts and their uncertainties, because I think this is perhaps one of the things where I feel that while we're still unclear about how to predict what will happen temperature-wise, we've got fairly good ideas, and this is some of the models that have come up in, this is a 2016 paper, 2014 paper, Fuss et al., that many of you will have seen before, and it makes various predictions for how temperature will change on the surface of the Earth. But what this will do in terms of impacts is much less clear. And I think I wanted to say a little bit about that. I can't go into all the impacts, but I'll talk in particular about sea level change. And what you can see is that business as usual has us going to very high degrees, numbers of degrees, like 4 degrees above pre-industrial levels by the end of the century. And we're on track for that kind of number right now. And these are the various alternatives that have to do with various levels of mitigation that various countries around the world need to put in place to actually address climate change. But to stay within, actually to get down to where we need to be, one of the things we need to be thinking about is net negative global emissions to get back down there. And so I want to talk about that as well a bit today in terms of what that means. Now, these temperature records are, of course, done with certain calculation of what temperature means relative to CO2. And I just wanted to go back and point out that right now we're at 425 ppm. And this is the record that I showed you earlier for the whole of the Cenozoic and actually the whole of the Phanerozoic. And you can see that actually that corresponds to a global mean surface temperature on this graph of about 19 degrees. And actually right now we're at our present day global mean surface temperature is 15 degrees. So there is roughly. So there appears to be some kind of a gap in terms of where we are, where the Earth is sitting in terms of CO2 and where its temperature is according to this geological record. So the question is, what does that mean? And of course there are a variety of things that are being thought about in terms of how you interpret that. But one of the questions is the Earth going to try and catch up with this? And are we actually going to be moving towards a much higher level of temperature increase than people have been predicting previously? So this is an ice core record. Not an ice core record. This is an ice sheet work that I want to show you, which has been done with Robin Bell at Columbia University. And you can see here that the effect of climate change has been that we're seeing a big increase in ice velocity, and this is just one example. There's also an elevation change here you can see developing, and you can measure this stuff with satellites and planes, and you can actually see what's happening to the elevation and seeing that it's actually decreasing as a result of changes in global warming, increases in global warming. The effects have been looked at in great detail by certain people over the last few years, and in particular, this is a rather nice paper produced by Rino et al. In 2018 in PNAS, and this shows you 4 blocks of time where they've got data, roughly a decade in each case. And this basically, this tells you what a gigaton is, if you're not sure what a gigaton is. A gigaton is roughly 400,000 Olympic pools. So this is about the equivalent of 100 million Olympic pools worth of per year coming off Antarctica, the Antarctic ice sheet. And Greenland is doing for different reasons, for various reasons, even though Greenland is much smaller, it's producing something comparable. So there's an increase in the amount of melting taking place at an incredible pace. And we don't actually understand too much about what will happen in the future with this. So a number of people, Rino is one of them, Richard Alley is another one, have talked in particular about the importance of iceberg calving, and Richard was actually at Lamont talking about this just this last week. It basically is to do with the fact that while we may be able to see what's happening in terms of gradual changes in ice sheets, what we don't know enough about is how quickly there will be catastrophic changes in ice sheets, where suddenly large amounts of material break off because of some feature that hasn't been very well thought about in terms of the strength of the actual ice sheet itself. And this could actually lead to much faster ice loss. This is a study that's just been published in Nature, showing Greenland ice sheet calving from 1985 to 2022, and you can see the rapid acceleration in this from the 2000s onwards in terms of the amount of material being lost from the ice sheets. So the effect of this, of course, is going to be felt differently around the world. The globe is not a bathtub, the oceans are not a bathtub. Certain areas where the ice sheets are being removed, actually those bits of land are actually going to increase, and the elevation is going to increase. So you can see some upward arrows here in places where there will be, downward arrows in places where actually the sea level effectively will be going down. But most of this, you can see that sea level is actually going to be going up. And the reason why you have places where it's going in the opposite direction is simply because you're taking mass off the land. There are other effects as well to do with sea level change, which I won't bother going into. But the net result is that certain places are going to be really badly affected, and you can see that this area, particularly around the equator and tropics, is going to be quite severely impacted. And that shows up in this study that was produced a decade ago, looking at which cities are most likely to be impacted by climate change, just using present-day estimates of defense and flood probability. And you can see that they're, of course, largely dominated by regions in the tropics and close to the equator, where you have large populations of people. And so this is just in terms of GDP and what does it actually do in terms of the damage and infrastructure to the place. So the future flood losses, this is not talking about loss of life, this is just in terms of economics, are huge in these areas going forward. Now, this is an example of some of the stuff. I can't go into all the impacts of climate change, but it's stuff that we don't know very much about how to predict going forward. What I want to talk about now is some of the stuff about emissions and what we do about this going forward. So this is a recent paper from there's an emissions gap report that comes out from the United Nations on a regular basis. This is a report for 2024 that looks back on greenhouse gases in 2023 and summarizes where they will come from. And you can see pretty much that most of it is associated with energy. There's some associated with land use, et cetera, and there is some stuff here that is sort of actually a mixture, I guess. So if you look at the energy consumption from fossil fuels, that's shown here on the left, and you can see that the proportion of our energy over time, and this is looking forward as well, the proportion from fossil fuels is going to decline as we build renewables. So this is, of course, a certain view of it, ExxonMobil Energy Outlook, 2018. But you can see that renewables are actually going to be growing. They may be growing much faster than Exxon would like to admit, but nonetheless, this is their prediction going forward. So this actually looks quite good. It looks like actually we're moving towards renewables, moving in the right direction. But the trouble is that proportion has got a denominator, and the denominator is the total amount of energy actually being consumed around the Earth. And that's shown here, and you can see that on the same scale, the total amounts of energy that we're producing is huge. And so that despite the switch to renewables, what we're seeing is still an increase in the usage of fossil fuels. So I'm not saying it doesn't matter that we're switching to renewables, I'm saying it's being outstripped by our growth in energy consumption around the world. And of course, a lot of that is to do with the need for countries to move out of energy poverty in particular. This shows you, again, the emissions gap report. you can shows you where most of the emissions have taken place in terms of total greenhouse gases. This is megatons of CO2. And you can see that, of course, China dominates. And if you look at it in terms of per capita, you can see that China is still very big, but United States, Russia are actually fairly large contributors as well. Okay, so getting yourself out of this is a question of how do you actually take the big steps needed to reduce CO2. And this is kind of what people have been saying we need to do to get to towards net zero. These show you the, this is just looking at what you need to do by 2030 and what you need to do by 2035. This is for different levels of temperature change. If we want to stay within 1.5 degrees Celsius, that's what we know to do. This is what, if we want to recognize we're going to be at 2 degrees Celsius, that's what we need to do. And this is kind of where we are in terms of this not making any change at all. And this is, in here, we have two kinds of things. We have orange bars are the unconditional agreements that have been made where people have actually committed to reducing their fossil fuel use, their emissions by a certain amount. And then there are conditional ones, which are dependent a little bit more on what happens elsewhere. So those are the kinds of ways in which they do these calculations. And what you can see is that this is actually where we are today in terms of where we are headed. And this is where we need to be in about 10 years' time. And this is the gap. And so the need to actually act to really do something dramatic is phenomenally urgent, of course, and dramatic, and of course is not being dealt with in the way that it should be. So this is an enormous challenge for society, and the IPCC, the attempts to try and get something done about this with Paris, of course, are sort of disappearing in the past a little bit in terms of people's commitments. So let's say a little bit about mitigation now and what you can do about it. And of course, you could say a lot about things here. One of the obvious things people talk about is to fly less. They talk about their personal contribution. And this does show that actually, you know, the emissions per person in terms of domestic flights, et cetera, are way higher than what we get from other sources of contributions to greenhouse gas emissions. And there are people moving fast on trying to decarbonize air transportation. So it was quite exciting at the Glasgow COP when Rolls-Royce announced that they actually flown an airplane with electricity, basically. And similarly, Rolls-Royce and others, Boeing, have been working very hard on developing sustainable aviation fuels. So there are these fantastic innovations taking place across the piece, and that's not to mention what's happening in many other sectors as well. However, the problem of aviation is tiny compared with this other part here. So we look at industry and power, transportation of other kinds, like, for example, road transportation, what we need to do in terms of agriculture, land use, et cetera, then those are much bigger chunks that need to be taken out. So you can take a look at the overall picture in terms of again, this is the previous diagram showing what we need to do to get down to net zero. You can take a look at the different sectors, and you can see which ones actually we need to do, which ones will actually bring about mitigation, and where there's potential for actually making changes to actually get ourselves down. And there's some overlap here between these guys, so industry and buildings with electricity production. And so there's a correction made there, and that adds up to 41 gigatons of CO2 equivalent, and getting there is going to be a massive challenge, but most of it's going to be around energy. So if we don't come up with solutions around energy, then we're not going to get to where we need to in terms of degrees centigrade. Now, the UN has also pointed out, and IPCC has also pointed out, that to really deal with this problem, we're going to have to eventually do negative emissions. There's no scenario that doesn't look at this and actually recognize that eventually we're going to have to do gross negative CO2 emissions, greenhouse gas emissions, to stay below 2 degrees Celsius, and certainly below 1.5 degrees Celsius. So there are a variety of things that have been looked at, and these are all areas where scientists are involved, academics are involved, new companies are developing like crazy. This is a Royal Society report produced on, and Royal Academy of Engineering report produced on greenhouse gas removal. And some of the ideas you've probably heard of before, there's of course, afforestation is one of them. People are less positive about that given the growth, well, a number of reasons why trees, forest systems, ecosystems don't seem to be as permanent as they used to in terms of forest fires, etc. So looking forward many years in the future, people are looking to see what can be done with some of these other techniques. And some of these techniques actually do involve separate storage mechanisms where you've got to put the carbon dioxide somewhere. Some of them involve carbon removal that actually involve so actually you're sequestering the carbon with the removal mechanism. So one of the ideas behind this, of course, is, or one of the ideas that's being looked at, is the idea of actually doing what nature does. So we've had this up and down record of temperature, and in the past we can see that at certain times, like here and here, we've got times when there was a lot lower CO2 in the atmosphere, much lower temperatures on the surface of the Earth. So how does the Earth actually do that? This is a paper that came out in Science in 2019, which is one of a few examples. There are several examples looking at the whole issue of how you take the continents and actually enhance weathering on the surface of the Earth. And this points out that actually a lot of the mountain belts where you have arcs in particular, which are volcanic arcs, which tend to end up being easily eroded and dissolved with weathering and take CO2 out of the atmosphere, but also where you have bits of the ocean floor that have been abducted onto the surface of the Earth and are also great places for reacting and taking magnesium silicate and turning it into magnesium carbonate. Those are actually located quite close to the equator today. And around the tropics, these purple bits. So if you look back in time to last time when it was really hot, 250 million years ago, you find those places where we had arcs and basically continental crust being created in volcanic systems and ophiolite abduction, etc. They were nowhere near the equator. If you look at times in the past where we had quite cold temperatures, like 300 million years ago and 445 million years ago, you can find the places where we had arcs and ophiolites when it was cold were located quite close to the equator. So the idea is that these are times when we had enhanced weathering going on the surface of the Earth associated with exposure of fresh basaltic and ultramafic crust at the Earth's surface. And so a number of people have thought whether this is one way of actually doing, accelerating this as a way of actually getting CO2 drawdown. There are other mechanisms. For example, people for a long time have been working on techniques for trying to take carbon dioxide directly out of the atmosphere, and direct air capture has been developing with a lot of companies taking interest in that and becoming commercial entities. There are others who are actually dissolving carbon dioxide in the interior of the Earth with hydrothermal processes. This is Iceland, which was work developed at Columbia University with Iceland, showing that CO2 can be trapped underground by mineralization, and similar work is still going on at Columbia in that area. But then there's this piece of work that's been developing over the last few years, and they've now applied this as another paper which came out just the other day, looking in particular at American farmlands and what would happen if you covered the surface of these farmlands with basaltic material and rock fragments that would actually weather quite quickly. And they actually calculate that with moderate costs, you can actually draw down quite significant amounts. Remember, we're talking about, we need to be looking at things that are in the gigaton range, and they reckon you could scale this to roughly the order of a gigaton of carbon dioxide per year with this kind of process. So these are the kinds of things that actually might make a real difference to the climate problem. And they require, this work was done in a university. So we need universities to be thinking about these large-scale ways of changing the carbon dioxide cycle that actually might make a major difference. So let me just finish quickly by talking about the role of universities in all of this. And in particular, I want to talk to you about Lee Bollinger, who was the president of Columbia University for 21 years, and he had developed a number of major initiatives. But one of the things he asked me to do when I moved to Columbia was he and the trustees asked me to look at the idea of what could we do further, given that we're quite strong in the area of climate, what else could we do in terms of, as a university? And the great strengths about being a university are that you have you're dealing with young people, and you're looking at one of the most important intergenerational human rights issues there is in climate change. You're also looking at the issues of justice, which are massively important in terms of modern universities. You're also looking at innovative transdisciplinary approaches, and universities have got that breadth of scale to actually, in terms of academic subjects, to really tackle something as complicated as climate change. You also have the fact that universities are trusted. They're trusted more than maybe lawyers, politicians, maybe many sectors of society in terms by the public. And so the considered opinion of academics can be really important in terms of doing something about this. A school is something that can build academic firepower. And the American university system, this is hugely important. So schools, institutes are great and all the rest of it, but schools actually have a way of hiring faculty, and they can actually also do something about building new kinds of curricula going forward. And so this is kind of why it seemed to be really important to be doing this, but particularly to be doing it in New York, where we had business leaders, policymakers, communities all interested in climate change. And actually we had, of course, Hurricane Sandy and the impacts of that. So it's no coincidence that actually we ended up setting up this new topic of managed retreat at Columbia. How do we actually deal with the fact that certain places are going to become uninhabitable going forward? And how do we deal with this in terms of organizing society to move people away from areas that are not going to work? So this is the kind of stuff that you can do. The climate school at Columbia is particularly important in terms of the strength it has already. We basically already, because of the Earth Institute, we had a lot of education programs that we were delivering in other schools. We already had the Lamont Doherty Earth Observatory and a number of other over 20 centers in the Earth Institute. So we had over 600 researchers and staff. And we had an $120 million annual budget already from the get-go, which is largely soft money obtained on federal grants. We also have a large amount of science that's been done there over the years and a lot of impact on UN IPCC thinking. So one of the things we really wanted to do was to see if we could take this further and actually build a school effectively from the Earth Institute and some of the other institutes that there are at Columbia University. And the idea of the school would be to have, of course, train a new workforce who are educated in climate. We did studies to check and see how important climate was going to be as a topic for executives going forward, how much they would need to know about climate. We also did work on trying to canvass students to see how important a climate change degree might be to them if they were to do that. Then, of course, we also want to expand the knowledge base for tackling the climate problem. And lastly, we wanted to find ways of working in ways that would really impact society. So this is just to show you how, when we started at Columbia, when I started in Columbia, I was fairly new. I'd only been there a year and a half when we started thinking about the climate school, less than a year and a half. And it was quite clear that actually nobody really knew much about how to build a school at Columbia because they hadn't done one for, it's 30 years ago now since they last formed a school. So a lot of it involved a lot of discussion and consultation at the same time as we wanted to get going quickly. So we decided not to move any departments around or anything complicated like that. We decided to work with what we had and just reorganize in terms of hiring faculty and putting in place the processes, the administrative processes, et cetera, to be delivering our own teaching, et cetera. And this allowed us to get going very quickly. We had a degree program that was already working, which I'll talk about in a second, which we could move from one of the existing schools back into ours so we could immediately offer degrees and get going. So we were able to get going during the pandemic without any massive increase in budget and just start with a school out of other stuff that we had. The focus of the school has been very much around building foundational knowledge, around mitigation and adaptation, and then also coming up with these ways of actually having collaborations that will actually allow us to address some of the major issues going forward. So the foundational knowledge stuff is focused in these three big areas. Firstly, sort of science and systems, energy systems, earth systems, etc. Secondly, social systems and justice, and what do we need to do about the climate from the point of view of carrying people with us and understanding the implications in terms of law and political activity, etc. Anthropology, arts and humanities that talk about how people feel and how they are. And then analytics. It's quite clear data science is going to be huge in this area. So these are the three big areas that we've been growing in that area, in climate. We're very concerned to try and focus our collaboration around in terms of action and impact in these particular areas. So these are the topics we've focused on: disasters, built environment, water, energy, food. You could do a variety of things. Food has been a major one of them. And then there are the education programs, and I want to quickly skim through what those look like so you get some idea. And again, we found that there was hardly anything in America that was called a degree in climate. In fact, there was next to nothing. So we took this degree program we had called the MA in Climate and Society, made that part of the climate school, and then we built two new degree programs that are just launching right now. One is an MS in Climate, which is a 2-year degree, which is a bit longer. The S is, we've now got approval for the first Masters in Climate Finance in America, which is just getting going. The MA in Climate and Society program is like this. It basically allows core degree subjects, electives, and then there are applied topics and capstones to be done to get your degree. And this is what we've seen in terms of the increased enrollments to this degree program. This is the one we took over from Arts and Sciences, when it was basically around 30, 40 people enrolled. And we actually switched that immediately as a climate school and had it up around 90, and now we're growing to over 100 students coming in to do this degree program. The MS in Climate is a different thing. It's sort of much more detailed. It has practical experience involved in it in the middle. But it's meant to give you a much more solid grounding, and the idea you might have this eventually, just like you have an MBA, recognized as a degree that gives you a qualification in law. This might become the professional qualification in climate. And the nice thing about this degree, this 2-year degree, is we can offer it with other degrees as well. So we've switched this to something that actually can be a dual degree with other universities or other institutions, other parts of the university. So we're partnering with other universities around the world to actually, so that they spend 1 year in their university and 1 year at Columbia University in New York, where they can actually switch over. Or even we can do this with other subjects that we want to get involved in. I was always impressed with Columbia when I heard that they'd started a master's in journalism and computing. I thought that was such an incredibly clever thing to do. And so now, of course, you can do these kinds of things in America in a way that is quite hard to do in a place like Oxford and Cambridge. This is the climate finance program. This has just been announced. We've only just got approval for it. So we're trying to launch it and get our first students in for this fall. And there's undergraduates as well. Let's not talk about that. So I just wanted to finish by saying I've shown you a lot of polar bears that are having a hard time, but there's a very positive side to this whole thing, and that is that we are, as part of a university, we have this amazing opportunity to help young people chart their future in a way that is more sustainable for the planet and for humankind. And it's these young people who give you a sort of sense of joy about what it is we're trying to do. And I do encourage people to think about this. What are the ways in which we can help our young people to really tackle this issue and get involved in it and actually build this subject for the future and for their future going forward. Thank you very much.